yeah, thank you for hosting this and for the opportunity to tell you all about what's going on with Einstein at Home. This is the first BOINC workshop I've actually participated in, but I've been involved in the Einstein at Home project since I began my PhD in 2013, where I was working in Hanover searching for gamma ray pulsars with Einstein at Home. I since moved away and did a postdoc, and then I'm now back in Hanover as a group leader, organizing pulsar searches, electromagnetic pulsar searches with Einstein at Home. So just to give a brief overview of the project. So this was a project that was originally conceived by Bruce Allen, who's also on the call and will hopefully correct me when I say wrong things. But it launched in 2005 during the World Year of Physics, with the goal of detecting continuous gravitational waves from previously unidentified neutron stars. And I'll explain a bit about what those words mean later in the talk. But since then, it's also been adapted to also search for pulsars in electromagnetic data from radio and gamma ray telescopes, in addition to gravitational wave data. And it's grown to be a very large BOINC project. So these numbers on the right are things that I just grabbed from our internal server page, just to give a bit of an overview. But we have about 42,000 hosts who have actively returned results in the past week, constituting about 400,000 CPU cores, in addition to around about 25,000 GPUs that are also returning results, giving us a total computing speed of about, according to some very rough estimates based on the number of work units that are being returned, of about 12 petaflops in total. And this is a project that has more contributors than I could list on a slide, so I've just left the link there. But it's being run by a dedicated team based in Hanover and also in Wisconsin. And I know that at least a couple of the Hanover guys are also on the call and can also correct me. But I think they're also going to be participating in the discussion section later about GPU programming as well. So yeah, as a brief overview of the science, I mentioned that Einstein at Home's goal is to search for new neutron stars. So I thought I should explain what a neutron star is. And this image here is one of the very few pictures of a neutron star that we actually have. So a neutron star is the core that's left over, the core of a massive star after that star has died. So when it runs out of fuel for nuclear burning, the core can't sustain the star against gravitational collapse, and the entire star basically implodes. The core becomes a completely solid core of basically nuclear material, and the outer envelope of the star kind of bounces off that core and creates this enormous supernova explosion. And this picture is an X-ray image of a supernova remnant, and what you see, the big cloud of stuff, is basically that material expanding into space and creating an enormous shockwave. And right at the very center of this, that remnant, you can see a tiny bright spot, and that is actually a neutron star that formed that supernova. But most of the time you can't see a neutron star. They're incredibly small. They're about 10 kilometers across, despite the fact that they contain more than the mass of the sun. And because they're so small, they basically don't emit very much light, and you can't normally see them, except in this case, this is a very, very young neutron star, so it's still extremely hot and visible in X-rays. But normally the neutron star has to be doing something else in order for us to detect it. And one of the things that we think neutron stars do is emit gravitational waves. So we believe that neutron stars are almost perfectly round, but if they are ever so slightly not round, slightly elliptical, then they actually they drag space-time around with them as they rotate, and that creates ripples in space-time that then propagate out from the neutron star. And now that we have working gravitational wave detectors, we hope to be able to detect those tiny ripples in space-time that are produced by the neutron star. And this has been the main goal of Einstein at Home, is to perform what we call blind searches, looking for new neutron stars, which we don't previously know exists. We don't know how fast they're spinning, and we don't know where they are. And we have to search for those signals. And those signals are incredibly faint. There are about, the signal we expect from a neutron star is tens of thousands of times fainter than the signals that we see from colliding black holes, which have been detected in the gravitational wave data. And because they're so faint, we basically need to integrate an enormous amount of data before that signal becomes detectable above the noise. And that means doing lots of very long Fourier transforms, basically, and basically trying to guess the exact spin properties of the pulse of the neutron star. So how quickly it's spinning, how quickly it's slowing down over time, and also having to guess its position in the sky very accurately. Just very recently, in fact, these two plots are from a paper that arrived on the archive yesterday. So Einstein at home sets the most sensitive constraints on the existence of gravitational waves from unknown neutron stars. If you know a neutron star, if you know where it is and you know how fast it's spinning, you can be more sensitive than when you have to do a completely blind search. But in terms of unknown neutron stars, Einstein at home sets the most sensitive constraints. And that's what this plot on the left is showing. This is just the upper limit on the amplitude of the gravitational wave as a function of how quickly an unknown pulsar might be spinning. And these red points are the new upper limits that have been set by Einstein at home. And that these limits translate to putting upper limits on how not round the neutron star can be, so how elliptical it is. And for obviously, the closer the neutron star is, the larger the signal is, and the easier it would be to see. So the upper limits on the ellipticity depend on our distance. And for neutron stars that are very close to us, we can actually set incredibly sensitive upper limits. So this red curve is for neutron stars that are about 50 light years away from us. And the magnitude of this signal corresponds to the equator of the neutron star deviating from a perfect circle by about the width of a human hair. So we know that there are not mountains on neutron stars that close to us that are larger than the width of a human hair, which is kind of mind-boggling. So these are new results that just arrived, are in the process of being published. And currently Einstein at home is performing targeted searches for gravitational waves from 3 neutron stars that we think exist in known supernova remnants, but whose spin properties we don't yet know, and are being searched on Einstein at home. The other way that we can detect neutron stars is if they are what we call a pulsar. So these are neutron stars with very intense magnetic fields, and because they have those intense magnetic fields and are rapidly spinning, they accelerate a plasma in the region around them. And that plasma contains charged particles, which then reach very high energies, and they start to emit gamma rays and also radio waves. And as the pulsar spins, the beams of gamma ray and radio emission kind of flash over the Earth and make the pulsar appear a bit like a lighthouse. And you can measure those flashes of light to detect the pulsar and also time its behavior. And the reason that we want to find lots of new pulsars is that they provide some incredible tests of lots of fundamental physics. So these are some examples of how you can test Einstein's theory of general relativity using pulsars. So if you have a binary system containing a pulsar, which is basically like an incredibly stable clock that you can time against, then you can measure very, very tiny delays in the arrival times of those pulses caused by different physical effects. So this plot on the left is showing the fact that the orbit is an ellipse, and due to general relativistic effects, the orientation of the ellipse is actually rotating over time. And the rate at which it's rotating over time is also speeding up because the system is losing energy in the form of gravitational waves. So the fact that this line is curved is evidence that this system is emitting gravitational waves. And then the plot in the middle is showing the delay in the arrival times of the pulses from the pulsar in this system as those pulses propagate past the companion star, which is also a neutron star. And you get an extra delay because the light is actually having to travel through a curved path through space-time. And then the plot on the right is showing lots of different constraints that you get from the masses of the 2 objects in this system by looking at different different general relativistic effects that you can see in the data. And the fact that each of these lines is a different constraint, and the fact that they all line up in the middle. Sorry, the two axes here are the masses of the two objects. And the fact that all these lines line up exactly in the middle tells us that general relativity is a self-consistent theory of gravity. And with Einstein at home, we're trying to find new systems that we can perform this work better with. So the more compact and the faster a neutron star binary system is orbiting, the larger the amplitude of all these effects are, and the more precisely we constrain the theories of gravity. And we know that there should be some very, very compact neutron star binary systems in the galaxy. And we know that because we know how often neutron stars collide with one another, because when they do, they emit gamma ray bursts. And we can see that happening in all sorts of galaxies across the sky, and we get a rate for how many gamma ray bursts there should be. And we know that that corresponds to roughly 1 gamma ray burst per Milky Way per 30,000 years. And we also know how quickly these systems evolve. And you can say that we can work out, if we know there is a system that's going to merge in 30,000 years, then its current orbital period should be about 10 minutes or so. And if you extrapolate that backwards in time, then we know there should be around 1,000 double neutron star systems with periods shorter than 2 hours, which is roughly the shortest known orbital period that we have, that we've seen from a known pulsar binary. So in theory, there should be thousands of these systems with very short orbits that we haven't found yet. And one of the reasons we haven't found them is it's very difficult to do. In order to find a pulsar in a binary system, you have to perfectly account for its orbital Doppler shift. And if you don't know what the orbital parameters are in advance, then you have to search over a wide range of those parameters. And that's what makes this problem computationally difficult and tackleable by Einstein at home. And so this is exactly what we're doing. We have several projects searching for radio pulsars on Einstein at home. We recently just finished a processing of all of the survey data that was collected by Arecibo, pointing along the galactic plane looking for new pulsars. So we finished that project just this year and have actually switched to basically performing exactly the same search with exactly the same code and the exact same search setup, but on similar data that was taken by the Green Bank telescope instead. And that processing is due to last a few months, at which point we'll then find a new data set to work on. But the Arecibo data has given us an enormous amount of computational work still to do. It returned about 60 billion pulsar candidates that we have to sift through. And we have a student at the moment who's working on identifying clusters within those candidates, which is what this plot is showing. Most of the candidates that we get are actually man-made interference signals, which look a lot like pulsars. So we have to cluster them out and hopefully find a pulsar, which is what this peak actually is. But even with this clustering and with feeding all of our clustered candidates through a machine learning classifier, we still have many tens of thousands, which is more than a reasonable PhD student can deal with. So we're in the middle of building a Zooniverse project to actually also outsource this candidate viewing process to citizen scientists as well. So we're hoping to get that finished in the next few months and get that underway. And in addition, we've also started a new search of different data coming from the Meerkat radio telescope, which is a new telescope. It's a prototype array that's going to be a prototype for the square kilometer array, which is currently being built. And it's now the most sensitive telescope in the southern hemisphere, surpassing previous telescopes by about a factor of 6 in terms of sensitivity to things in the southern sky. And as part of the TRAPPISM project, which stands for Transients and Pulsars with Meerkat, Meerkat was pointed at several globular clusters, which are very dense regions of space where there's a very large, dense population of old stars and also of pulsars. So the idea is you point a radio telescope at one of these clusters and there's a very large chance of finding lots of pulsars rather than just one. So Einstein at home is currently searching for pulsars in very short binary orbits in 3 globular clusters. And the other remaining thing that Einstein at Home is doing is searching for gamma ray pulsations as well. And that's a very different deal from searching for radio pulsars, because the gamma ray data that we have is very sparse. So this is the best view that we have of the gamma ray sky, which comes from the Fermi Gamma Ray Space Telescope, which is this satellite that I've shown here. And this image is actually integrated over, I think, 12 years of data. And even then, we're still finding new point sources, which we think might be pulsars. And from a typical pulsar, you maybe see 1 photon per week or so, if you're lucky. So in order to detect pulsations in that, you need to properly predict all of the rotations of the pulsar over a 12-year span. And that requires guessing lots and lots of parameters with very high precision, making this extremely computationally expensive. But this is something we've been doing for years, and Einstein at Home has already found 39 new gamma ray pulsars. We currently have 1 survey ongoing running on the CPUs on Einstein at Home, which is our 5th iteration of the Fermi Gamma Ray Pulsar search, hence this acronym FGRP5. And these are the 14 new pulsars that we found in that iteration of the survey, which is currently winding down. It's on the last few lowest priority sources. But once that finishes, there's now a lot more data than there was when we started this iteration of the survey, so we can repeat the process and hopefully find lots of new pulsars. And the other ongoing gamma ray pulsar search on Einstein at Home is running on GPUs, and it's searching for binary gamma ray pulsars, which is even harder because, again, you also have to properly account for the pulsar's orbit. And in that case, we actually rely on having optical observations of the star that the pulsar is orbiting. So we can measure the orbital period by looking at changes in light from the star that the pulsar is orbiting. And with those constraints, we can then reduce the parameter space that we have to search in order to find gamma ray pulsars. And so far, we found 2 new Black Widow specific types of binary systems with Einstein at Home. But these are by far the most computationally demanding pulsar searches that we do on Einstein at Home in terms of computations per source that we're searching. I was also asked to give a bit of discussion about BOINC itself. I'm a scientist. We have a great team of people who do the BOINC details behind the scenes. So I'm maybe not best placed to talk about this. But I asked them for some input for this about things that Einstein at Home might be doing differently to other projects. One of the things that they highlighted is that we believe Einstein at Home supports at least as many or more platforms than any other project running on BOINC. Some non-scientific evidence for that is that we have more logos on this table on the BOINC website than any other project, but that includes some kind of more niche and unusual processing architectures like the Intel GPUs, Raspberry Pis, and also native support for the new Apple silicon CPUs. We also think we're doing some kind of unusual validation that many other projects aren't doing or might not be suited for doing, in which case we can be a bit more flexible or a bit sloppier than other projects, in that we already accept that we don't have 100% sensitivity to the things we're searching, so we kind of accept a low probability of having invalid results coming back. We do something called adaptive replication, where hosts become trustworthy over time, and then we no longer require those to be binary validated against other results coming from other hosts. And we also don't require our results to be perfect binary matches of one another. The results that we get back from our searches are lists of candidates, and sometimes different architectures can return, due to rounding errors and so on, you can have those candidates coming in different orders and so on. And our validator is built to be kind of flexible in terms of spotting those. And yeah, there was also a couple of requests or things that we could discuss in terms of things that would be useful for BOINC to support. One of those is that it was a request to allow projects to change their master URL. Apparently that's difficult to do without volunteers having to unsubscribe and resubscribe to the project. And apparently Einstein at Home is currently using an old URL that we would like to update, but are not able to easily. And the other thing, which I guess is a topic for the discussion session later, which is that we're not currently supporting Apple Silicon GPUs on Einstein at Home, but that could give us another chunk of computing power that would be very useful to have. I believe there's support for that in BOINC now, but it's not something that we've built into Einstein at Home yet. So it's kind of a new thing that is worth discussing now. So yeah, that's everything I wanted to say, and I'll just leave a very brief summary on the screen and say thank you for listening.
Thanks very much, Colin. That was terrific. With other talks, if anybody has questions, please use the hand raise feature. It's under reactions, hand raise if you have any questions. In the meantime, I'll start with one. You mentioned when you're processing the results, in some of these data sets, you're using a machine learning classifier to flag candidates, and in others, you're using Zooniverse. And I'm actually quite curious, what are you finding the human classifiers to still be outperforming the machine learning? Like, what different kinds of problems are you giving to those two projects?
Yeah, so we haven't started the Zooniverse project yet. We're building it at the moment. And actually, in that case, the candidates that we will pass to Zooniverse have already gone through a machine learning classifier to reduce the number to something manageable. That machine learning classifier was originally built to classify results from the same survey that we're reprocessing on Einstein at Home. So it's kind of already perfectly designed for that problem. But certainly it's not perfect. We know that based on, we have already been vetting these candidates for whenever we do these pulsar surveys, and we know that we have to give it a very conservative threshold for what it considers to be a possible pulsar, because it can miss stuff, and it's often very hard to tell the difference between a pulsar signal and man-made interference, or hard to write an algorithm that tells you that. But we humans spot that quite quickly. But yeah, I'm very interested to see how the Zooniverse project goes. I think it will be very useful in terms of getting sensitive human pattern recognizing eyes onto as many candidates as possible.